Let us now continue with part P, the results and the perspectives. So here we will first look at the computation of the population, the individual systems, then an overview of statistical results, and then we will come to the comparison with observation and finish with some perspectives and conclusions. So actually before we left out this part, which is to draw and to compute the synthetic population. And this might actually be one of the most interesting parts to see how the predicted synthetic populations or systems actually first come into existence. And we will do that again by using now the generation 3 Bern model, but you could do that, of course, also for all other global models. And the setup we will use is the following. So we'll study formation of planetary system around solar mass stars. We'll do that for 1,000 systems, 1,000 stars, disks. And we will assume that in each disks, we have 100 embryos, planetary embryos, which have a mass of 1 lunar mass. And we will put them in at t=0, uniform in the log of the semi-major axis from the inner disk edge out to 40 AU. And here's some important parameters. The alpha viscosity is 2 × 10⁻⁻3, and the grain opacity reduction factor in the protoplanetary atmosphere is 3 × 10⁻3. And the outcome we will look at, there are many ways of looking at it, but one is the mass distance diagram of here one individual system. You here see the initial conditions, the metallicity, the initial gas mass, initial solid mass, and then here you see the predicted system here, where here we have gas-dominated giant planets. We can have volatile-rich planets with hydrogen helium, so Neptunian planets. We can have volatile-rich planets without hydrogen helium, so this would be water worlds. We can have something, a planet type we don't have in the solar system. This would be iron silicate planets with hydrogen helium. There is none in this system here. And then there are iron silicate planets without hydrogen helium, so something like like Earth-like planets. When we have these gray points, these are protoplanets which were lost during the evolution process. So this is the last position before they were accreted by another more massive protoplanet. Or this is an example. This here on this axis. These are those which have migrated into the host star, and we have also some which were ejected out of the planetary system. And finally, here you maybe see this bar here, this horizontal bar. This shows the period to apoastron distance. So this indicates the eccentricity. And this would be the state here at 5 gigayears. It's of course very interesting to see how such a global model behaves. How does it show? How does it indicate that such a planetary system comes into existence? And this is we can do here by studying how this initially 100 planetary embryos, how they grow, migrate, and interact as a function of time. So here we start at t = 10⁴ years with the following initial conditions. So 1.7% solar mass gas disk and 57 Earth masses of solids, and this corresponds to a low solid mass. And now here we see these 100 embryos uniform in log, and the color code is the ice mass fraction. And now we will let them grow, and you see how the masses are growing. This crosses means that there is a giant impact, the embryo collision. Sometimes therefore they go up. Here we are inside of the ice line where growth is faster, but it's stalled because there are not many solids available here. Here outside of the ice line, growth is faster, so is initially slower, but then we can grow to larger masses. But now here the disk mass, the gas mass has already disappeared because it's a low mass disk also. And what has happened at the moment when the gas disk has disappeared, the orbits have the damping has stopped, and there was a number of giant impacts. You see these edges here, these jumps. This is always one giant impact, and now we are already at the end, and we have ended up with a system of 1, 2, 3, 4, 5, 6, 7, 8, 9 or so super Earth planets. Inside they are rocky, and outside they are water rich, and we have some leftover planets. But here we should keep in mind that we have integrated this growth only for 20 million years. So over longer time scale, there will certainly still be some growth out here. And we also see that these planets have some, but not huge eccentricity. And this is actually the first class of architecture that we find. These are quasi in situ Earth and ice-formed systems. So these are systems which only contain low-mass planets. Migration did happen, but the fundamental ordering that we have inside dry planets and outside we have volatile-rich planets, this remains. So this is one example. Here we have again mass, another example than what we saw here, but it's the same. And we can also see that the planet mass is increasing in the inner part, and this is because we have more solids outside than we have inside, and then it goes down again because the growth time scale becomes longer and longer, so we don't have time to grow. And this is the mass distance diagram, and this is the same system but now in distance radius diagram. And here we see that despite the relatively similar masses, the planets which have a lot of ices, and even more so those which have hydrogen helium, these are those here, they are much bigger than the planets which are iron silicate planets. This is another example, again, a little bit this increase, but planet mass is relatively similar. Here again, these are similar, then we have a strong jump. And here we have now a third one. Here the masses are again similar, and in this case also the radii are pretty similar. So this is actually the most frequent outcome. These are systems only of Earth and super Earth, and the typical mass scale here is set by what we call the Goldreich mass. So this is the mass the planets get from the giant impact phase, where their eccentricities are given by the mutual interaction with the other planets. So the eccentricities are pumped up till they correspond to the escape velocities, the mutual escape velocities of the protoplanets, and this sets an effective width of their feeding zone, and this in turn then sets the masses. So here it's really more or less in situ, and it is really the solid growth which sets the architecture. And let's move on to a little intermediate mass. So 100 Earth masses, this is about in the middle of the distribution, and let's see what we get here. So the beginning is very similar as we have seen before. So first grows in the interior, and slower growth initially outside of the ice line. This jump is at the ice line. Still here already have some giant impacts. But here now something happens that didn't happen before. Once the planets start to migrate inward, this happens once the migration time scale becomes shorter than the growth time scale. The disk is still there. Therefore, they migrated all the way in. They also pushed. There was a time where there was a huge resonant chain, and this pushed in the planets. Here we also have some planets which then disappeared into the star because of tidal interaction of over long time scales. You also saw some planets where the mass went down after this dissipation. This was because of atmospheric escape. And here we are left with a system of super Earth or sub-Neptunian planets rather, a little bit more massive than we saw before, and the mass is more or less constant as a function of semi-major axis. And if we look at some more examples, so here we have one where we see the masses, and here we have the radii. Here the masses are similar, but the radius here is much bigger because these planets could keep the hydrogen helium while the close-in one could not. This is another one. What you can see here is that here the mass as a function of distance, or also here the radius, is maybe decreasing, while for class 1 it was increasing, and this has to do with the time when the planets start to migrate inward. It's earlier and at higher masses for the inner planets than for the outer planets. And this here is a third example which shows quite a strong piece in the pod effect, which is actually recovered in these simulations. Now let's move on. Now we go already to the rather high initial solid masses, 245 Earth masses, and let's see what happens here. So at the beginning, it's still similar, but the scale is already bigger. Here you see some dynamical interactions, some giant impacts already still when the disk is around. Here this still looks similar, but so they grow more or less in situ first, then the migration time scale becomes short. And now what has happened, and this is the difference, was that one of these planets, when it started to migrate in, it was sufficiently large to trigger gas runaway accretion, and therefore its mass started to grow quickly. It went into type 2 migration, which is much slower than type 1 migration. So here we end up with a system with 3 inner super Earths or sub-Neptunian planets, 1 giant planet at around 1 AU, about 1 Jupiter mass, 2 outer Neptunian planets, and here again some smaller planets. But this system is certainly not dynamically finished. After 20 million years, you see this very high eccentricity here. So we could expect that these planets would still continue to grow. So this is now a mixed system where we have inner low mass planets and then giant planets. And here we see quite some diversity. Here we have a system where we have 2 inner lower mass planets, water Earths, 2 giant planets of relatively different masses, and then some slow mass planets outside. This is a very different system, only 1 giant planet. Here we have an inner planet, a rocky planet with hydrogen helium, quite massive, 10 Earth masses at 0.1 AU. And here we have something which is a little bit like the solar system, 2 giants, the outer a little bit smaller, and inner planets, but of course it's not really like the solar system because the masses are bigger. We have also Neptunian planets inside here, and also the masses of the giant planets are larger. So the difference here is basically that here the mass scale is such that while these proto-giant planets start to migrate inward, they are massive enough to trigger gas runaway accretion. But dynamically, there are some eccentricities, and you can see that sometimes there are some planets which were scattered or which had a collision, but this is less frequent than in the next case that we will see as the last cases. And these are now the very high solid masses, 327 Earth masses. And let's see what happens here. At the beginning, it's similar, but the growth is now really fast, telling you that this is not a very realistic initial condition if it evolves so fast away from the initial conditions. And what happens here now is that instead of only 1 planet triggering gas runaway accretion, we have 2, and shortly afterwards a 3rd. And if we have 3 giant planets, this is closely together, they typically become dynamically unstable, and this is exactly what has happened. So we have here 1 planet which fell into the star. Here we have 1 which was ejected. Here we have other 2 which were ejected or fell into the star. And in the end, we have only 1 very massive, it's about, I don't know, 20 or so Jupiter masses on a very eccentric orbit. And this is the last class. These are dynamically active giants. Here we have a system with 2 giants, and maybe there are sometimes some leftovers, something like maybe like a Kuiper belt, some outer leftover planets. Sometimes they are very eccentric, like this one. Here we have a lot of planets which were ejected. So these are all these planets here. And sometimes it also looks like that. So there is also quite a diversity. But what is typical, or what is always the case, is that there is no inner low mass planets. And this was now a demonstration of different outcomes on the system level. But now let's look how it looks at the population level. And for that, you can basically look at a similar movie as before, but now overplotting all 1,000 systems together. And this is what we then find. So we see what we have seen before, the inner growth, then here the growth of the giant of the planets which become giants. Then later on, we have this ice-rich planets which migrate in. Now we are look at the evolution over long time scales. Here we see effect of atmospheric escape. Here we see the effect of stellar tides. And this is then what we have in terms of the population. And this, when we then plot it at 5 gigayears, this is how it looks like. And what we see is that when even without going to the details, we can see that I would argue that some fundamental features of the observed population can be recovered. And for example, there is a large population of close-in low-mass planets, which in the synthetic population is actually an overlay of 2 separate cases. So these were these dry class 1 systems and these migrated in class 2 systems, which might explain a number of observations. Then here we have a cold Jupiter population we have less planets in between, we have distant super Jupiters, and we have, of course, things which we cannot observe nowadays, like these ice worlds here. Probably here, the model is limited in its predictive power because we only integrated the systems for 20 million years, so we must be careful with planets which maybe still grow more. And we have also planets here in the habitable zone. But there are also disturbances like here, the hot Jupiters, which are absent in the synthetic model, and we come back to that later. And we see something which was already seen in the Ida and Lin models, is that the variation of the disk initial conditions over a range likely occurring in nature leads to a large diversity of planetary system, which is similar as it is observed. Let's continue a little bit with some fundamental statistical results before we go then to the comparison with the observations. So first thing you can ask is, how many planets do we have on average per system? And what is found is that this synthetic planetary system contain on average 8 planets more massive than 1 Earth's mass. So this is not so different from the solar system, but this includes all orbital distances. Therefore, we cannot yet really tell observation. Then the fraction of system with giant planets is 18% at all orbital distances, but the systems are quite compact. Only 1.46 are at more than 10 AU. And these systems with giants contain on average 1.6 giants. So there is about the same number of systems which have 100 about each, which have 1 giant planet or have 2 giant planets. And this result is independent of the number of embryos we put in the beginning into the disk. We looked at the 100 embryo case, and but you see that this is really the same independently of you have 10 or 100 embryos. And note that only about 5 stars out of 1,000 have 3 giant planets because of orbital stability. And now for the low mass planets in the habitable zone, so there we find that 44% of stars have such a planet, and typically the multiplicity of these planets is rather low, 1.3. And this is due to the fact that the habitable zone is actually not very wide, not in semi-major axis. And the mean metallicity of stars with such planets is minus 0.11, so it's solar. So these are systems that are different from the solar system. Most of them, not all, but most of them, in the sense that typically these are systems with only low mass planets, with habitable planets, but there are also some mixed systems like in the solar system. So these are these results, and the next question is probably now talking about the link to the disk properties. What sets the outcome? And as you could guess from these different classes that we talked about before, the most important initial condition is the mass of solids, of planetesimals initially present in the disk. And this we can see here. So what we have here on the x-axis is the initial mass in solids that we have in the disk at the beginning, and on the y-axis we have the final total system mass. So for each system, these are 1,000 points. Each point is the sum of all the planetary masses in this system. And then here we can also plot these gray lines, which are efficiencies, if you wish. So this would be an efficiency of conversion of 10%. This would be 1, and this is 10. And why this is more than 1? This is because we include here the hydrogen helium. Therefore, we can go above 1. And what you can now see is that when we have very low initial solid masses, then we also end up with this low initial total system masses, and the conversion efficiency is maybe about 30–40% or such. And then once we reach something more between 100 and 200 Earth masses, then this is when we can start forming the giant planets, and therefore the total system mass goes up relatively quickly. And if we go even further up, we get very massive systems which contain really massive giant planets here. We can compare that with the solar system. We can say, okay, the minimum mass that the solar nebula had in solids, we can get it by summing up what we think are the heavy element content in the planets nowadays. So maybe 20 Earth masses in Jupiter, 15 in Saturn, we don't know so exactly, but you end up with something in this domain here, and the total solar system mass is then here. And we see that we need about 2 to 3 times the minimum mass solar nebula in order to form the solar system, which is of course possible because this is only the minimum that we can see nowadays in the planets. We can take this figure a little bit further and bring in again the architectures. And we can do that by now color coding for each system the number of planets in a system with a mass of at least 1 Earth's mass. And then we see the following. So at the lowest initial solid masses, the number of such planets is 0 or very low. And this is just because there is not even enough mass to build one planet of at least 1 Earth's mass. If we then move here, we get to systems which contain a high number of planets, more massive than 1 Earth's mass, sometimes up to 20 or 25, all low mass planets here. And then if we continue further, suddenly we go up here and the giants come, and you see that the number is again strongly decreasing. Here in the transition zone, there are still systems with giant planets and maybe 10, 15 or so planets in total. But as we move to even higher initial masses, here we get into the domain of the class 4, so the dynamically active giants. And here you see that here we have often systems which there is only 1 or 2 giant planet left. And these, by the way, are systems which start with a lot of solids, but in the end, all the massive planets were ejected, and we have this kind of very strange system where, despite these huge initial conditions, we don't have a lot of planets in. So I think with this plot, we can quite well understand how this initial mass of solids affects the outcome and the system architecture. The second most important initial conditions is, by the way, the external disk photo-operation, which sets the disk lifetime together with the viscosity. And this one depends on the stellar burst environment and affects also the emerging system architecture, which is known actually observationally since recently. These were all, I would say, interesting theoretical results. But of course, the point of population synthesis is then to see how it compares with observations. And this I want to show you with a number of examples. There could be many more. So we start first with a comparison with the Harp Survey. The HARPS, this stands for High Accuracy Radial Velocity Searcher. So this is a radial velocity instrument, and we used it back in the early 2000s to 2011 about in the GTO survey to observe 822 solar-like stars. And what is important is that we know the observational bias. And it's interesting to compare this result with a series of papers which came out just now on the California Legacy Survey. But this is the result from the Harp Survey. So we have period versus mass. Points are the detected actual extrasolar planets, and the lines are the detection probabilities. We saw that already in the first part of the talk. And now we can count what we found. So we found 161 planets, around 102 stars, giving a mean multiplicity of 1.6. And now let's apply this population synthesis method to our generation 3 prediction, the one that we saw before with 100 embryos per disk. So first, we have to zoom in to the smaller periods because, of course, we don't have the very long period planets. Then in the next step, we apply the sin-i effect, assuming that the orbits of the planetary systems have a random orientation. And then we apply the synthetic detection bias. And then this is now what we predict what HARPS would have found if it had not observed actual 822 planets, but 822 stars, but 822 synthetic stars or systems. And we can again maybe overplot that with the actual observations. And I would argue that we can see that we see, of course, the bias. There's nothing here, but we see a certain concentration here and probably also a certain concentration there. And we can again count now for the synthetic planets. And although you maybe don't see it, but there are actually about twice as many black points. So here we predict we would have discovered 317 planets, around 204 stars. And if you divide that, you also get the multiplicity of 1.6. And now we can start to do some comparison, first a little bit quantitative. So I would argue there is a similar global structure with some voids, with some concentrations. And the mean multiplicity is also an agreement that this is a hint of the prevailing system architecture. But of course, there is this disagreement in absolute numbers by a factor 2. This could be linked to the initial conditions. This could be linked to some parameters. But when we compare the absolute numbers, this is always a little bit more sensitive to parameter choices than, for example, something like a multiplicity. And you also see another disagreement. This is these hot Jupiters here, and it could be that that we miss here physical effect in the model, namely that in the model we neglect quasi or high eccentricity migration plus tidal circularization, and this would indicate that these hot Jupiters were actually formed via this channel, which is not included in our current model here. But let's try to be also a little bit more quantitative. And this we can do by looking now at the mass distribution. So this is the mass distribution of the detected planets. In black, we have the synthetic ones, and in red, we have the actual discovered mass distribution. And here we see, of course, mostly that we have many more synthetic planets. This is this factor 2 difference, but we can normalize it so that the total number is the same. And then we can compare. And what we see first is that we have this fundamental bimodal structure, and we have especially also a change around here at around 20 Earth masses, and I think this is a smoking gun of core accretion. So this is the runaway gas accretion, which sets in when the core mass and the envelope mass is about each 10 Earth masses. And by the way, it could in principle also be the pebble isolation mass, would probably lead to a similar prediction, but there are also opposites new for this interpretation. In terms of differences, we see first that the giant planets, the synthetic ones, are too massive, and we also see that we have too few intermediate mass planets, and this is nothing else than the planetary desert in Ida and Lin, and it keeps coming up in many, not only ours, but also in many other actual synthetic planetary population, because it's so inherent to the core accretion paradigm. So we have to understand what is going on. And these 2 points, of course, increase both point towards too fast gas accretion. And what is interesting here is that we tested this for different ways of describing the gas accretion rate in the disk limited regime. This would be important here, derived from several 3D hydrodynamic models, and this always gave the same. And here it's important to remember that when you set up such a 3D simulation and then you derive some fits for the resulting gas accretion rate, you cannot test what it would make when you use it within such a global model. You just get these results, but you don't know where they lead to or what they mean as a prediction. And here we see that for all these hydrodynamic models, we get a similar result of 2 massive planets. And this could mean that there should be additional other physical explanations, that these models are in principle right, but that there are other assumptions are maybe not fulfilled. For example, it could be that these disks have a much lower viscosity than we assumed. It could also be that magnetic fields regulate the gas accretion. There could also be an angular momentum barrier, or there could also be 3D circulation, which was maybe not sufficiently resolved in these models here. So you see that we can here really put such models to the test, and we can also say, okay, we can beyond going saying, oh, it looks similar or something like that. No, we can even quantify the discrepancy between theory and the observations. And I think this is very important given all the effort that observers are making into also giving us quantitative constraints. And therefore, I think formation theory is now able with population synthesis to do also such quantitative statements. Now let's move on. Comparison is the Kepler survey. It is, of course, one of the most important constraints also. And here, this is from a little bit an older generation of the models compared in Mulders et al. 2019. And here you have the observed period versus radius. And these numbers here are bias corrected occurrence rates, like for here below the valley, here above the valley, here warm or coldish giants, and here hot Jupiters. And this we can again then compare with the synthetic result. And we see that for most classes, there is a similar numbers, except that we have not enough of these planets here, of these sub-Neptunian planets. And there is also some other discrepancies. And I forgot to mention that in absolute numbers, we again find a too high occurrence. Here it's even a factor 5. This could also be something with how to apply the bias, but it goes certainly in the similar direction. And we also see that here in this population, the valley is not really well visible. We have other population where it is, but unfortunately, I don't have the time to talk about that today. Let's go to an even other one. This is statistical comparison with direct imaging. This is the Shine survey at the VLT, and we saw the results of before for GPI by Nielsen et al. And here we should keep in mind that we probe a very different kind of planets and also different observable. So the luminosity, not the mass or the radius. And this here is now the actual detection by sphere with the sensitivity map. And this is a comparison of the synthetic population, semi-major axis versus J-band absolute magnitude. Because here the magnitude or the magnitude contrast has already been converted into companion mass, but the Bern model also gives directly and self-consistently the magnitude of the planet also at young times, young ages, and in principle one should rather compare this. In any case, if we just look at the fraction of FGK stars with planets in this interval here, then this is the observational result and this is the synthetic result. That's maybe a little bit on the lower side, but still in agreement. So the overall frequency is similar, and also the mass luminosity relation where we have that, like beta pictoris B, is actually similar, but this you cannot see in this plot here. Now, these distant giants in the system, these were mostly from class 4 systems. So these are single massive eccentric planets from scattering events where sometimes there is another inner giant planet and the mean metallicity eccentricity is pretty high. So while we have here, it seems maybe a similar frequency, we certainly cannot reproduce something like an HR 8799 like system with distant massive giants on not very eccentric orbits. And this is a hint that maybe there is something else at play also, like maybe structured disk allowing the formation of giant planets further out, maybe pebble accretion allowing growth further out, although this is also not so clear if it's really possible. And then because of orbital migration, bringing the planets in. And it could also be, of course, that some of these planets form by gravitational instability. And here we could go on by comparing more complex things like distance eccentricity, mass distance eccentricity relations, and so on to further investigate. So I see I'm running out of time. So I'm sorry I had to speed a little bit up, but I hope I could give you a little bit an impression, first impression only, of what we can do in terms of such statistical quantitative comparisons. Let me now finish with the perspective and the conclusions. So here we have to keep in mind that it's an observationally driven field. Therefore, if we look into the future, we should mostly consider the coming missions, which will be of interest for this statistical approach. And I think here, of course, it looks very bright because soon we will have Gaia, where we expect an enormous number of giant planets in this regime here. And then later on, we will have the Roman, the Nancy Grace Roman satellite, which will discover about several thousand cold low mass planets, mostly around M dwarfs. So the future is really very bright, looking at all the coming statistical observational constraints. And with that, we really have an exquisite knowledge of the planetary mass distribution and the demographics in this regime, now also at the intermediate masses. And this will be really great to test with that the mechanism, theoretical ideas about gas and solid accretion. And it, of course, doesn't stop here. Later, we will have Plato and then also Ariel, where we then can even test a lot of things like the mass radius relations of the interior, and then finally also the statistics of atmospheric compositions. And I think what this means is the following. So if you have here again the mass distance diagram, this sometimes reminds me of something like that. So this is a very old map of the Earth. I don't know in which years it is exactly. So the United States would be up here. Canada is not known. Then this is South America, but this is really very poor. Of course, Europe is there, and also the Far East. We don't really know. So, and this is what we have, I think. For some parts, close-in planets, we have some good understanding from the demographics, but a lot of parameter space is currently not yet well known. But I would say that by 2030, we have something which is maybe a little bit similar as this one. There is still Australia as Terra Australis incognita, so they didn't know what was going down here. So still, we will not still have some white parts on this map. But still, I think what will happen is that by then, we will have the possibility to cross-check the same theoretical models with population synthesis, many different, and especially currently unexplored parameter spaces. And I think with that, this will be the key to understand whether our theory really captures the governing underlying physics, and is not merely a sophisticated, tweaked fit to explain what we already know. We will see. And it's clear that much can be done here on the theoretical side. I think of the initial conditions, the early phases, the disk models, hybrid pebble planetesium models, the link of the formation, atmospheric composition, trying to really understand what is going on with this gas accretion. And I think what is the additional point of which I unfortunately couldn't speak today is this chance of observing planet formation as it happens, like PDS 70, which will hopefully yield a completely new direct class of constraints for planet formation theory. And with that, I'm coming to the conclusion. So population synthesis is a tool to compare theory and observations and to improve our understanding of planet formation. So here we can really try to use the full wealth of observation constraints that we have. We can put theoretical models to the observation test, which is often difficult otherwise, and we can also see the global statistical consequences. So which processes are key in shaping planetary systems? We can derive observation constraints on many processes, solid and gas accretion rate, n-body direction, or orbital migration links. And we see the link between the disk and the planetary properties, which might become much more important also in future. Instrument-wise, we can also use it to predict the yield of future instruments and space missions. And one thing is very important to keep in mind. We saw these models from the 70s, and of course now we have very different ideas about the underlying physics. And it could well be that in the future they will think the same about our current models. Therefore, the population synthesis depends on the progress of the formation theory. It's not a done thing. And we have a lot of many new theoretical developments to test, and fortunately also a lot of new observation constraints and observation to come. So I think it's really great when we look into the future. What I would also like to show are here some resources in case you're interested in more information. And with that, I would like to thank you very, very much for your attention.